Today we shall see applications for Michael-Nerod theorem. First we can prove this corollary using the Michael-Nerod theorem, and then can see two different applications for this corollary. And the corollary is that a language R over an alphabet set sigma is regular if and only if the canonical equivalence relation is of finite index. I hope you remember this equivalence relation from the previous lecture. Proof. First we can try to prove the if case, that is, if it is of finite index, then the language must be regular. Suppose the canonical equivalence relation is of finite index. Now recall that the only property of Michael-Nerod relation which is not satisfied by the canonical equivalence relation is the finite index property. I hope you remember from the previous lecture. Now you assumed that this is satisfying the finite index property also. So definitely this must be then a Michael-Nerod relation. So if this is a Michael-Nerod relation, we can apply the construction that we discussed in the lecture L23 to obtain a deterministic finite state automaton for this language. And since there exists a deterministic finite state automaton, the language must be regular. So we proved that if it is a finite index, the language is regular. Now the other case, only if, we have to prove that the language is regular only if this relation is of finite index. We can try to prove it by applying the method of contradiction. For the purpose of contradiction, assume that this is of infinite index, that is, this relation is having infinitely many equivalence classes, but still R is regular, which is the opposite of that. Now, by taking this assumption that R is regular, we can see that there exists a Michael-Nerod relation for R. Why? Because we proved in lecture L22 that for every regular language there exists a DFA, and from that DFA you can obtain a Michael-Nerod relation. So this is true. Now from the lecture L24 we know that any Michael-Nerod relation must refine the canonical equivalence relation. This is what we proved in the previous lecture. Okay. Now from the refinement relation we know that the number of equivalence classes of this relation is greater than or equal to the number of equivalence classes of this. That is what I have written here. It is the property of refinement. Now if that is the case, you can conclude that the canonical equivalence relation has only finitely many equivalence classes, because here we show that the number of equivalence classes of this relation is more than the number of equivalence classes of this. And because this is a Michael-Nerod relation, it follows or it satisfies the finite index property, and here you have only finitely many classes, and that number must be greater than or equal to the number here, and therefore this must be finite. And now you are getting this contradiction. You started with assuming that this has infinitely many classes, and you concluded that it has only finitely many equivalence classes, and hence proved using contradiction that the language is regular only if this relation has finitely many equivalence classes. Now both if and only if cases have different applications. This can be used to prove that a language is regular. That means If you want to prove that a language is regular, you just prove that there are only finitely many equivalence classes. If you want to prove that a language is non-regular, just prove that there are infinitely many equivalence classes. Applications. Applying Michael-Nerod theorem to prove regularity. Consider an example. Look at the language L, where a string is in the language if that contains odd number of A's, that is it. We know that this is a regular language, but now we are going to prove it using Michael-Nerod theorem. So, it is enough to prove that the canonical equivalence relation is of finite index, that is corollary 1 says. Now, to get the number of equivalence classes, you need to recall the definition of the relation. Two strings x and y are related by the canonical equivalence relation if and only if for all strings z, if you append z to both x and y, this is the case. Both are in the language or both are not in the language. Now, which are the equivalence classes of this? Now, we can see whether x and y are related when both contain even number of A's. That is the case that we are taking. Suppose x and y contain even number of A's and Z be an arbitrary string. There are two cases depending on the number of A's in Z. First case, suppose the number of A's in Z is odd. Now we can see that the number of A's in XZ, that is an even number plus an odd number, must be odd. In this case as well, an even number which is in Y plus an odd number is odd. So, both strings XZ and YZ contain odd number of A's, and then by definition of this language, they both are in the language. Now, the other case when Z is containing even number of A's, you can see that XZ will contain even number plus even number and even number of A's. Similarly, YZ will contain an even number of A's, even number plus even number, which is again an even number. So, both are containing even number of A's, and so by definition both are not in the language. So, we are proving that when both x and y, if xy is a pair of strings containing even number of A's in both x and y, then for all z, when you append the same z to x and y, the resulting strings are both in the language or both not in the language, and hence x and y are related. So, we proved that x and y are related when they both contain even number of A's. So, that is the first equivalence class, the set of all strings with the even number of A's. Now, similarly, you can get the next class, that is odd number of A's. You consider two strings x and y both containing odd number of A's. Apply the same trick, you can prove that x and y are related. For the interest of time, I am skipping this part. From my explanation, you can watch it and see. So, the second class is the set of all strings with odd number of A's. Now, any string, if you take from sigma star, will be either in the first class or in the second class. That is very easy to see. So, maximum 2 classes, and there are only finitely many classes. And if you want, you can also prove that if you take a string from the first class, that is y, and a string from the second class, that is x, you can prove in a similar way that x and y are not related. But that is not required for this particular problem, but if you want, you can prove. So, only 2 or less than 2 classes are there. So, this has finitely many classes, and hence you can conclude from the Michael-Nerod theorem that this language is regular, because the canonical equivalence relation is of finite index. Okay, that is the first kind of application. Now, the second kind. applying the Michael-Nerod theorem to prove non-regularity. That is, you have to prove that certain languages are non-regular by applying the Michael-Nerod theorem. Example, prove that the language a raised to n, b raised to n, where n is not greater than or equal to 0, is not regular. This is not to be a non-regular language. Now we are going to apply Michael-Nerod theorem to get a proof. It is enough to prove that the canonical equivalence relation for this language has infinitely many equivalence classes. So now we need to look at the equivalence classes. To find it, recall the definition of the equivalence relation that you might be knowing now. Now look at the set of all strings. Now you can have a claim which says that for all natural numbers I and j, when I is not equal to j, that means I and j are two different natural numbers, then you can prove that the strings ai and aj must not be related under this canonical relation. You can prove it. Suppose I is not equal to j, that is I and j are two different natural numbers. Then look at this. Suppose you append the same string b raised to I to both a raised to I and a raised to j. What will happen? The first concatenation will give a raised to I followed by a raised to I. It is in the form in the language, so it is in the language. And a raised to j, b raised to I is not in the language when I is not equal to j. So we proved that whenever I is not equal to j, the strings a raised to I and a raised to j are not equivalent. So the claim is proved, and now you can use this claim to prove that there are infinitely many equivalence classes, because you can get infinitely many pairs of natural numbers which are distinct and which are not the same. For example, you take 1, 2, then 2, 3, then 3, 4, the successive pairs. All these are different, and when they are different, you will have different equivalence classes, and hence there are infinitely many equivalence classes of this relation. And this it follows from the Michael-Nerod theorem that the language is non-regular. See, you can use MNT to prove that a language is regular and also to prove that a language is non-regular. It is enough to just find the equivalence classes of the canonical equivalence relation. If there are finitely many, say that it is regular, otherwise you say that it is non-regular. Okay, now moving on to a different corollary for the Michael-Nerod theorem, which says that there exists a canonical deterministic automaton for any language. So that is beautiful. We are not now looking at just regular languages. For any language, there exists a canonical deterministic automaton. How will you prove it? You know that you have an algorithm which will take, if you take this algorithm that we discussed to generate DFA from a Michael-Nerod relation, and see that this may not be a Michael-Nerod relation, but even then this algorithm will give you an automaton. And when it is non-regular, this is having infinitely many equivalence classes, and hence you will get infinitely many states in Q. And if it is regular, you will have only finitely many states in this automaton, and hence the automaton will be a finite state deterministic automaton. If it is having infinitely many equivalence classes, you will get an automaton with infinitely many states. But in both the cases, by definition, you are getting a deterministic automaton for the given language, regardless of whether the language is regular or not. So this is a nice application for Michael-Nerod theorem. It tells you that for any language, you are getting a deterministic automaton for that language. If it is regular, you will get a finite state automaton, otherwise you will get a deterministic infinite state automaton. You can look at an example. You know that this is a non-regular language, and I will give you a deterministic automaton that I obtained using the MN theorem. And we can prove that these are the different equivalence classes. AK, when you substitute a value for k 0, 1, 2, 3, etc., you will get a separate class. So, infinitely many classes in AK. Similarly, here also infinitely many classes, and this is a single class. For the interest of time, I am not explaining what these classes are, but given this, you can easily verify that these are in fact different equivalence classes. And now, if you apply this construction, you will get this these states. These are the states. This correspond to the first set. When k is 0, you will get epsilon as the string, the corresponding class, and this is k is equal to 1, the corresponding class, k is equal to 2, the corresponding class. Likewise, it goes infinitely many classes in that row itself. Now, this is the other one, that is where the number of A's and B's are related by this relation, and these are all the classes. And you can see that this is the initial state, and these are all the transitions, and the final state is again final state is 2. These two are the final states. So, equal number of A's and B's, and epsilon is also accepted. Because of the interest of time, I am not explaining why all these are different classes. That I am leaving as a homework exercise. You can just verify. So, that is a beautiful application where you can find deterministic automaton for any language. Now, the third corollary of the MN theorem, which is saying that if L is regular, then the automaton that you can construct from the canonical equivalence relation, which is now a Michael-Nerod relation when L is regular. This is a Michael-Nerod relation, and if you apply the construction to get an automaton, that is the construction that we discussed in the lecture L23, then what you are obtaining is the unique minimal DFA for that regular language. This is also a very nice result. See, if the language is regular, then you look at this canonical relation, which is a Michael-Nerod relation. Apply the construction to get an automaton, then what you are getting is the unique minimal automaton. Proof. Now, on this relation, when you apply the construction, you are getting an automaton, and because there are only finitely many equivalence classes for a regular language, you are getting a DFA for that language. We can verify that the equivalence relation used by the state minimization algorithm that we discussed, this is that equivalence relation. Two states of the DFA P and Q are equivalent or collapsible when for all Z, the string for Z from both P and Q are going to final states or both are going to non-final states. So, that is automaton. Sorry, that is the relation of our states in that automaton. And now, you can verify that when you obtain this automaton, this relation is identity. That means P and Q are related if and only if P and Q are the same state. So, you cannot collapse. So, this we can verify, and this is the third corollary. With this, we are coming to the last part of this lecture, where I am giving you 3 practice problems for you to practice and understand what we did today. First is, by applying Michael-Nerod theorem, prove that this language is regular. Second one, using Michael-Nerod theorem, prove that this language is non-regular. This problem is tricky. You have to come up with an idea to prove that there are infinitely many equivalence classes. Then the third one, apply the state minimization algorithm on the DFA which you obtain from the canonical equivalence relation for this language. So, you obtain the canonical equivalence relation for this language, find the equivalence classes, then you obtain that automaton, and then you verify that this is the unique minimal automaton. How will you verify? Try to apply the state minimization algorithm. You can see that you will not find any pair of states to be collapsible. With this, we are finishing this lecture. So, today we have seen applications of Michael-Nerod theorem. So, we can prove regularity, we can prove non-regularity, we will get a deterministic automaton for any language regardless of whether the language is regular or not. And also we show that when you apply the automata construction on the canonical equivalence relation for a regular language, what you are getting is the unique minimal automaton. Thank you.